Hi, my name is Justice Adamson, and in this video we're going to talk about using the normal tissue constraint during inverse optimization and some of the details there. And this is for Eclipse treatment planning system version 16.1. All right, let's get started. So here I have a plan in Eclipse, and we will go into the inverse optimization, and I will show you some of the details for the normal tissue parameters. All right, so here we are in the optimization. And you can see on the bottom here, we can see the normal tissue objective on the right here. And there's a couple of options. There's off, manual, and automatic NTO, and then this auto SRS NTO. And NTO standing for normal tissue objective, right? Automatic NTO, this is, basically you don't have to define anything except for the priority. You tell it, how strong of a priority to give it relative to your other optimization criteria. And then it figures out everything else for you. And the manual says that it kind of adaptively decides some of these criteria based off the plan, and that may work just fine for like a standard prostate or just kind of like a standard plan. I do a lot of radiosurgery planning, so we kind of set our own criteria, and so I'll often use this manual setting. We also don't have this SRS criteria, which we'll set these to kind of be very specific for radiosurgery cases. And so let me just tell you a little bit about what these other ones do. We have distance from target border, dose, start dose, end dose, and fall off. Now you can see that these here will control what this curve here looks like on the right. And what this curve is basically kind of like an ideal fall off curve. It's, I think, a good way to think about it. It's expecting the dose to start at 100% of your target dose, and this is distance from the target, right, on the x-axis. And so, and distance from basically any target. And here is dose as a percentage. And now let's say you have different dose levels in your plan. It's going to choose the lowest dose level that any target has. So basically, if you've got like one that's getting 2 gray per fraction and one that's getting 2.5, this is going to be kind of 2 gray. And so first let's play with this distance to target border. So for instance, I may use 1 millimeter or 0 millimeters or 2 millimeters or 3 millimeters. And basically that's going to define where it's kind of allowing the dose to be at up to 100% before it starts to fall off. Moving down to the bottom here, we've got this fall off. So this is basically a measure as to how fast that curve is going to fall off. And you can see here that that this will change quite a bit, going from like 0.1 to 0.5, and I think probably that's a decent range to look at, is somewhere in that range, like 0.1 to 0.5. Somewhere in there is going to be the values that you're usually going to use. And your start dose, this is again relative to that target max dose. So I could say 100% here, 0 millimeters here, and 20%. This is telling it that, right outside the target, it's okay for it to be, at 100%, but then it's immediately going to fall off drastically, and then down to like a 20% dose level, and basically, if it exceeds this, as for any points in the body, they're going to be there's going to be a criteria on that to penalize that. And so this would be like one extreme. You could have maybe a 5, let's say a 3 millimeter margin, and make this like a 35%, and 0.1 here. This would be kind of another extreme here, where now you're allowing kind of 100% of your dose out 3 millimeters past any of your targets, and then kind of a much broader fall off down to kind of a higher dose level, right? So that's kind of how this is working. This would be less stringent. You would be much more stringent if you had this closer and falling off quicker, right? And I think there's different scenarios where those would be appropriate. And then again, this priority here is going to kind of, for the entire normal tissue constraint, kind of push that up and down. And yeah, that's kind of the basics for a normal tissue objective. Thank you.